So let's talk about Galois extensions. So we had this lemma last time, we'll start from there. Let k over f be a finite extension. Then saying that k over f is normal and separable is equivalent to two other things. One is the equality of three numbers, the order of a certain group being equal to the order of the number of embeddings from k to the algebraic closure of f, fixing f pointwise, and being equal to the degree of the extension k over f. And again, it's also equivalent to saying that each a in k satisfies a polynomial in fx that when you go to the bigger polynomial ring kx splits into distinct linear factors. So in particular, the minimal polynomial of a has all distinct roots, and all these roots are available in k. So that already tells you, C already tells you that these are very nice extensions. And B already shows you that there is some nice connection between group theory and field theory. The order of this group is equal to the dimension of this vector space k over f, which is a field theory object. And Galois theory exploits this connection in a very beautiful way. So normal and separable extension will be called a Galois extension. So if you're sticking to finite extensions, then you could make any of these the definition of a Galois extension. And in this case, the group k over f, ought k over f is called the Galois group of the extension. It's denoted by gal k over f. So let me give some examples. We haven't quite proved these, many of them. Well, the first few you can prove by hand quite quickly. So this is very straightforward. You take the smallest non-trivial extension, a quadratic extension, degree 2, that splitting field of x squared minus 2. And there the Galois group is z mod 2. What can you do to construct an automorphism of q root 2 to q root 2? You can send root 2 to its conjugate, which is minus root 2. That's the non-trivial element that generates this z mod 2. And similarly, you could consider r over c. That's again degree 2. It's a splitting field of x squared plus 1. So again, here it's z mod 2, obtained by sending I to minus I. So the Galois group in this case is the identity and the complex conjugation map. If you send I to minus I, that means you're sending z to z bar. And the fixed field, you see, is the real numbers. If you move beyond these, then the one that we have seen kind of in detail is the splitting field of x cubed minus 2. So that's a degree 6 extension obtained by adding a cube root of 2 and a cube root of unity. And here I claim that the Galois group is the symmetric group of 3 letters. We kind of indicated how to construct some of the elements of this Galois group. Basically, it has 3 roots. This polynomial has 3 roots, and this has 3, just permutes the 3 roots in whichever way you please. Then one very important example that I want to list is the cyclotomic extension, at least in the prime case. I can write it down very straight easily. So zeta p is e to the 2 pi I over p. And this is a degree p minus 1 extension, and it's a splitting field of the polynomial 1 plus x plus up to x to the p minus 1. Well, zeta p satisfies x to the p minus 1, but that is not irreducible. It factors like x minus 1 times that factor. And that factor is irreducible by, it's a standard application of Eisenstein's criteria. So this is a degree p minus 1 extension. I think the Galois group is z mod p star. And this we need to prove. And then actually we have seen another one, this finite field extension. So P is a prime number, and you could take the finite field of order P to the n. That's an extension of Fp of degree n. And this we know is a splitting field of this polynomial. We constructed this field as splitting field of this polynomial, in fact. And there actually, so this is degree n, the Galois group is just Z mod n, and I know the generator. It's this thing that we wrote down. Takes an element to its pth power. Sigma of A is A to the P. Remember, that's an automorphism of the field. It's called the Frobenius. And that has order n in this Galois group, because when you raise it to the, apply it n times, so A goes to A to the P. When you apply sigma again, A to the P, do it n times, it will be A to the P to the n, but that's A, because A is in this, which satisfies every element of this field, we remember, satisfies this polynomial. So A to the P to the n is again A. Yeah, so that's why this has degree n. And you can show that that generates the Galois group. So these are some examples. These are all finite extensions. When you go beyond finite extensions, the theory is considerably more subtle, and we won't talk about it. But you have, like the mother of all extensions, Q contained in Q bar. Well, that's an infinite extension. So these are all algebraic numbers, remember. And this is the, oops. This is the splitting field of, let's say, all polynomials in Qx. Because all the algebraic numbers are available there, so all polynomial in rational coefficients factor into linear factors in this field. And this Galois group is sort of the mother of all Galois groups as far as extensions of rational numbers are concerned. This is called the absolute Galois group of Q, and it's an incredibly complicated and rich object. It's arguably, I think not arguably, it is the most important group in number theory, and arguably the most important group in all of mathematics. I mean, the properties, understanding this is sort of the holy grail of number theory, you might say. And some of the deepest problems in number theory are related to understanding properties of this Galois group. It plays absolutely a central role. So you can morally think of this guy as the set of symmetries of all rational or integer coefficient polynomial equation, of all roots of all these polynomial equations. Okay. Maybe we should get down to earth and actually indicate how this lemma is proved, a little bit at least. So I claim, let's try A implies B or B implies A. Let's try A implies B. So I claim that in any case you have these inequalities. This number is always less than or equal to this number, is always less than or equal to that number. This we know already from stuff we talked about in separability. And this is true because if you give me one embedding, so let sigma be some embedding of k in f bar fixing f pointwise. Okay. So sigma k to f bar embedding such that its restriction to f is identity, then I can produce this many embeddings just by precomposing with the automorphisms. So if you give me an element in aut k over f, means it's automorphism from k to k fixing f. So then tau then sigma is another embedding. So if you have 5 things in this group, I can produce 5 embeddings if you give me one embedding, sigma, by composing with those 5 things, tau 1, tau 2, etc. So that's why the number of these embeddings is at least the number of these automorphisms. Okay. And now, why this equality? So this is equality holds if and only if k over f separable. And here I claim equality holds if and only if k over f is normal, meaning a splitting field extension, because then you also know that any embedding is actually an automorphism. This fact that we kept on quoting. So here equality if and only if k over f is normal, meaning a splitting field extension. So if you have both, then you have equality in both places. On the other hand, if you have equality in both places, these are if and only ifs, right? So if you have equality here, then it's normal. If you have equality here, then it's separable. So that's the equivalence of A and B. And the equivalence of A and C has essentially already been quoted, so I'll skip that. So now we are almost ready to state the fundamental theorem of Galois theory, which is sort of the last thing that I want to talk about. But we'll have to get there. To prove it, we'll need a few lemmas. So we'll first state those lemmas and develop them, and then get to the theorem.